Let's have a look at conversion between number systems. So up to this point, we have looked at converting binary numbers to decimal and decimal to binary numbers. We've looked at converting decimal numbers to octal numbers and octal numbers to decimal. We've looked at converting decimal numbers to hexadecimal numbers and from hexadecimal numbers to decimal numbers. But what about converting hexadecimal octal numbers to binary and vice versa, and maybe even converting hexadecimal numbers to octal numbers and vice versa? So we're going to be looking at that, and essentially you've got the skills already to be able to do this, once you see the methodology to follow, and so it's quite easy to do. The first conversion we're going to be looking at is octal number systems to binary. Okay, so the highest number that octal numbers have got is 7. Okay, and 7 representing a binary number is equal to 111. Okay, so therefore it's 3 bits that are being used, and so therefore what we do is with the octal number, each number we're going to represent in 3 bits. Okay, so let's have a look at an example. Let's say, for example, you've got the number 7352. Okay, so first thing you're going to do is you're going to look at a 7. That's 7 over there. How do you represent that into a binary number? Well, that is 111. Okay, then we look at the next number, which is a 3. How do you represent 3 in a binary number? Well, that is 011. Then the next number we look at is a 5. How do you represent that 5 into a binary number? Well, that is a 101. Again, all the binary numbers we're looking at is sets of 3 bits. Then the number 2, how do you represent that in a binary number? Well, that is a 010. And that is your answer. It's pretty straightforward. All that you do is you look at each digit, convert each digit into 3 bits for a binary number, and then you put them all together next to each other. Let's look at another example. So let's say you've got 615, because that's the octal number, this is the octal number. And you've got to convert that to binary. Okay, so again, what is 6 in binary? Well, 6 is 110. What is 1 in binary? Well, that is 001. What is 5 in binary? Well, that is 101. Okay, and that is your final answer. Okay, so it's pretty straightforward to do octal to binary. Let's have a look at converting binary to octal. So a very similar procedure would be followed, just inverse. So we've got the whole strings of 1s and 0s. So 1 1 0 1 0 1 1 1 0 0 1 0 1, for example. Okay, so what we do is we're going to separate this into sets of 3 bits, and we're going to start from the right hand side. Okay, so over there we've got 3 bits, 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 and then we've got 1 bit over there. Because now this bit over here, if we had to place 2 zeros in front of it to make it 3 bits, it's not going to change the value of this number. Okay, so again, what's 001 from binary to a decimal number, or in this case would be an octal number? Well, that would be equal to 1. What is 101? Well, that is 4 plus 1, which is 5. What is 011? Well, that's 2 plus 3. 2 plus 1, which is equal to 3. What is 100? That is equal to 4. And 101 is equal to 5. Okay, and therefore that is your answer. Let's have a look at another example. So again, bunch of 1s and 0s. 101011000000101. Okay, let's have a look at how to convert. So again, we're going to split up into 3 bits, starting from the right hand side. So we're going to have 3 over there, we're going to have 3 over there, 3 over there, 3 over there, and again 1 bit that's on its own, so we're placing 2 zeros in front of it. Okay, so what is 001? Well, that is a 1. What is 010? That's 2. What is 110? That's 4 plus 2, which is 6. What is 000? That is 0. 101 is 4 plus 1 is equal to 5. Okay, and that is your final answer. Okay, so it's very much straightforward to do. Okay, let's look again at now converting hexadecimal to octal numbers and, or sorry, hexadecimals to binary numbers. Okay, so hexadecimals to binary. Okay, so with hexadecimals, the highest value that you can get is the number 15, or F. Okay, and 15 is represented in binary as 1111. So therefore, the highest value that we're going to have is going to consist of 4 bits of 1. Okay, so now we're going to do exactly the same thing as we did with the octal number system, but we're going to be working with 4 bits. Okay, so let's have a look at an example. So you've got the hexadecimal number 7CA5. Okay, so that's your hexadecimal number. Okay, what is 7 in binary? Well, 7 is equal to 0111. Again, 4 bits that we're using. What about C? Okay, now we've got to look at the table. So I'm going to just write over here A, B, C, D, E, and F. That's equal to 15, 14, 13, 12, 11, and 10. Okay, so C is a 12. Okay, so 12 to be representing a binary number would be, it would be 8 plus 4 and 2 zeros. Okay. What about A? Well, A is the letter that represents 10. So 10 in a binary number would be, or that would be 8 plus 2. So 1010. Okay, and finally 5. Or 5 to represent in a binary number is equal to 0101. And that is our final answer. Okay, let's look at another example. So let's say we've got the hexadecimal of D, E, A, and F for deaf. Okay, so D. What is D in binary? Well, D is 13. So 13 would be 1101. Okay. What about E? E is equal to 14. 14 is equal to 1110. Okay. What about A? A is equal to 10. So 10 will be represented as 1010. And F is equal to 15, and that's represented as 1111. And that's your answer. So again, very straightforward to do. Okay, what happens if we want to convert binary to hexadecimal? Again, a very similar fashion of that you're going to have to do. So 101101011101, for example. Okay. So now we're going to split it up from the right hand side into sets of 4 bits. Okay, so we've got 4 bits over there, 4 bits over there, and we've got 3 bits over there, which means we can place a 0 in front of it to make it 4 bits. Okay, so 0101, well, that's equal to 5. Next 4 bits, 1010, well, that's equal to 10. 1101, well, that's equal to 8 plus 4, which is 12, plus 1, which is 13. Okay, Now obviously we can't represent it in this fashion, so we've got to look at our table again and just make sure that things correlate. So 10 is A and 13 is equal to D. Okay, so the final answer is 5A D. Base 16. Okay. Let's have a look at another example. So let's say, for example, we want to look at 1 0 1 0 0 1 0 1 0 0 1 0 1. Okay, so again we're going to split it now up into bits of 4, starting from the right hand side. Okay, so we got 4 bits over there, we've got 4 bits over there, another 4 over there, and the 1's on its own, so we need to have 3 zeros in front of it. Okay, so what is 1? What's 0 0 0 1 at least in a decimal number? So that is equal to 1. 0 1 0 0, well, that would be equal to 4. 1 0 1 0, well, that's 8 plus 2, which is 10. And 0 1 0 1 is equal to 4 plus 1, which is equal to 5. Okay, so that's equal to, because we've got a 10 over there, so we need to replace it with an A. So that's equal to 1 4 A 5. Base 16. Okay, so it's a very straightforward process. Same principle applies. You would with Octal, it's just we're working with 4 bits. Okay, so now that we've done that, let's have a look at the next conversion. So we want to convert from hexadecimal to octal numbers. Okay, so again, this is going to be, and this is probably the only time that you're going to convert from hexadecimal to another number system, and then from that number system to octal. You never do that ever with any other number system conversions that you might be involved with. Okay, so let's have a look at the example. Let's say we've got 7CA5, and we're going to convert that now to octal. Okay, so the first thing we've got to do is we've got to convert this number into a binary number. Okay, so this was one of the examples we've actually had to look at before. So to convert this to a binary number, it's going to be 0111 1100 1010 0101. Okay, so that's in binary. Okay, so now what we're going to do is we're going to split this up into bits of, well, into sets of 3 bits. Again, from the right hand side. So that is 3 bits. We've got over there 3 bits. Got over there 3 bits. Over there 3 bits. And over there 3 bits. Okay, and we're starting off with a 0 over there, so we don't have to worry about that much. That's not going to make any difference. Okay. We can place 2 zeros in front of that if we want to, but it's not going to make any difference to our final answer. Okay, 111. What's that equal to in a decimal number? That's equal to 7. 110. Well, that's equal to 4 plus 2, which is equal to 6. 010. Well, that's equal to 2. 100 is equal to 4. 101 is equal to 5. Okay, so keep in mind that's in base 16, so that's your answer. Okay, so again, this is very much what you've seen before. We're just going to take it one step further and use that binary number to convert to another number system. Okay, let's try again the example that we looked at. We had to look at DEAF. Okay, and DEAF, remember we got the number that was, if you convert this into binary, that was going to be 1101, 1110, 1010 1111. Okay, so that's in binary. Okay, so now again we're going to split it up into bits of 3. Okay, so we've got 3 over there, 3 over there, 3 over there, 3 there, 3 there, and this one is on its own, so we place 2 zeros in front of it. Okay, so what's 001? Well, that's 1. What's 101? Well, that's 5. What is 111? That's 7. 010 is equal to 2. 101 is equal to 5. And 111 is equal to 7. Okay, so that is our final answer. Okay, let's have a look at an example where we're going to convert from an octal number to so from octal to hexadecimal. And you could probably see over here the steps that we're going to take with this. It's going to be pretty much the same. So again, let's look at the example where we're at the octal number 7352. Okay, so 7352, if you recall correctly, we went and we converted this into binary. That was equal to 111, 011, 101, and 010. Okay, so now we're going to go and break this up into bits of 4 from the right hand side. Okay, so it's 1 2 3 4, 1 2 3 4, 1 2 3 4. Okay, so 1110, what's that's equal to? 14. Okay, 1110, what's that? It's again 14. And 1010, well, that's equal to 10. Okay, so what's 14 again equal to when we look at our tables? Remember, we look at our table over here quickly, and remember 14 was equal to E, 10 was equal to A. Okay, so that means that this is equal to E, E, A, base 16. Okay, let's have a look at another example. So we had to look at the number 615. It was an octal number. Okay, so 615, when we converted that into binary, we got 110, 001, 101. Okay, so now again we're going to split it up into sets of 4 bits, starting from the right hand side. Okay, so it's going to be 4 bits up to there, 4 bits over there, and then we've got this one on its own, so we're going to add 3 zeros in front of it. Okay, so 0001 is equal to 1. Okay, 1000 is equal to 8. And 1101 is equal to was 8 plus 4, which is 12, plus 1, which is 13. Okay, and again that's equal to, so 13, if you look at the table, that would be a D, so that's equal to 18D, base 16. Okay, so as you can see, same steps were followed as we would do from hex to octal, or octal to hex. It's just the number of bits we looked in the binary number that would identify what our answer would be. Okay, then finally another number system is one that we haven't covered before, but it's one that you're probably going to come across as well. It's a binary coded decimal number. This is also known as BCD. Okay, so if you look at your decimal numbers has got the maximum number that is equal to a 9. Okay, and a 9, which is in binary, is equal to 1001. Okay, so that means that we're going to need 4 bits to represent a specific number. Okay, so let's say we want to convert from decimal to BCD. Okay, so let's say we've got the number 5923. Okay, so 5 in binary, which should be of 4 bits, would be equal to 0101. Okay, 9 in 4 bits is equal to 1001. 2 in 4 bits is equal to 0010. And 3 in 4 bits is equal to 0011. And that's our answer. So not base 2, this is BCD. Okay, let's have a look at another example. Okay, so we've got the number 6574, because these are base 10 numbers and we want it to be converted to BCD. Okay, so 6. What is 6 in binary? Well, that is 0110. Okay, what's 5 in binary? Well, 5 is 0101. 7 in binary is equal to 0111. And 4 in binary, or at least again in sets of 4 bits, is equal to 0100. BCD. That's our final answer. Okay, so what would happen if you wanted to convert from BCD to decimal? Okay, so we're going to look at the at a number of, let's say, 10110 1000 1001. Okay, so this is our BCD number, and we want to convert this into a decimal number. Okay, so again, we're going to split it up into 4 bits. So we've got 4 bits over there, we've got 4 bits over there, we've got 4 bits over there, and 1 on its own. Okay, so we know there's 3 zeros in front of the 1. So 0001 is equal to 1. 0110 is equal to 6. 1000 is equal to 8. And 1001 is equal to 9. That's our base 10 answer. Okay. What about, let's have a look at an example of 1100 0000 100. Okay, so this is BCD. Again, we're going to convert it now into decimal. So we're going to go with 4 bits again. So we've got 1, 2, 3, 4 bits over there, 1, 2, 3, 4 bits over there, 1, 2, 3, 4 bits over there, and again we've got the 1 on its own. Okay, so now we're going to convert each set of bits to its decimal value. Okay, so 0001 is equal to 1. 1001 is equal to 9. 1000 is equal to 8. And 0100 is equal to 4. Okay, and that's base 10. And that's our answer. Okay, so up to now, and up to this point, we've looked at converting between binary, octal number system, hexadecimal number system, how to convert between them all, and then also we've now looked at binary coded decimal numbers. So we've basically able to convert in between all different number systems. We have not looked at decimal numbers for or fractional numbers in hexadecimal or octal number system, or even in BCD number system. That is not something that I feel is needed. There's a little bit more advanced things to look at. But the principles that we've looked at up to this point is essential ones that I think is needed, and that are often used in computer systems and programming later on that you would also experience.